Okay, hi guys. So in the previous lecture, we were seeing the Arrhenius equation for general irreversible reaction, and we saw that the relationship between K, which is rate constant, and Arrhenius parameters, and it was something like K equals to A e to the power minus E upon RT. We also looked at the graph in which we looked at 2 points, which is T1 K1 and T2 K2 in the graph, and for the same we can write that ln k1 would be equals to ln a minus ea upon rt1. Similarly, ln k2 would be equals to ln a minus ea upon rt2. So from both these reactions we can write, or both these equations rather, pardon me, both these equations we can write that ln k1 minus ln k2 would be equals to ea upon r t2 minus ea upon r t1. So this can be written as ln k1 upon k2 would be equals to E upon R 1 upon T2 minus 1 upon T1. Okay. So please remember this form. This is a very important formula. Okay. So now next we will look at the graph of log of K versus T. So the graph would be looking like, on y-axis let's say we have log of K, and on x-axis we have T, or let's say T inverse. Then we can write that slope would again be equals to minus minus E upon 2.303 R, because we have converted LA into log, and similarly you can find the intercept value. Okay. So we had an assumption before deriving this equation that EA and A, which was the Arrhenius parameters, were considered having negligible change during the course of the reaction, but in reality EA and A both depend on temperature, and both the values actually increase with temperature. EA and A depend on temperature, and both EA and A value increases with increase in temperature value. Okay. And greater the value of EA, more the effect on rate constant. Okay. And next let us see some example wherein we already know that ln k2 upon k1 would be equals to EA upon R 1 upon T1 minus 1 upon T2. It can also be ln k1 upon k2 it's equal to EA upon R 1 upon T2 minus T1, whatever may be the case. You just have to shift the minus sign on any side of the equation. So for a particular reaction we did an experiment in which, in first experiment, we got T1, we took T1 as 300K, and we got some rate constant, and secondly we took T2 as 375 Kelvin and we got some K2, and we did another experiment in which first we took T1 dash as 320 Kelvin and we got some K1 dash, and secondly we took T2 dash as 335 Kelvin and we got some K2 dash. So we have to compare the ratios between K1 by K2 and K1 dash upon K2 dash. So from this, K2 dash upon K1 dash can be written, rather K2 upon K1 would be proportional to the difference of 1 upon T1 minus 1 upon T2, which would be 300 times 375. And in numerator we will be having 75, and in this case K1 dash upon K2 dash will be proportional to 300 times 335, and in the numerator we would be having 335 minus 300, which is again 35. So clearly K2 dash, so this is K2 dash rather, K2 dash upon K1 dash. Okay, so clearly K2 upon K1 is greater than K2 dash upon K1 dash. Okay, now let's see some more on pre-exponential factor, which is A. So we can write that A is a measure of rate of collisions irrespective to their energy. Is a measure of rate of collisions irrespective to their energy. Okay, and let us see what is activation energy. Or EA. So this is the minimum kinetic energy that reactant molecule must have in order to form products. Minimum kinetic energy that reactant molecules must have in order to form products. Okay, so with this we come to the end of this lecture. In the next lecture we will be continuing on seeing more on Arrhenius equations. So till then, good luck and goodbye.